Hey there, guys. This is Mr. Sheeline. This is going to be the lecture video for the Unit 7.2 notes, considering or going over sound waves. This is only going to be like normal. This is only going to go over the content inside the inside the notes. It does not go over the check your understandings. There's a separate video where I go through all the check your understanding. So make sure you check out that while you are working on the check your understanding. So let's go ahead and get to this. So, okay, remember, let's kind of review here. Interference. What is interference? Remember, this is a wave or a pulse traveling through a medium, and it will reflect upon whatever the fixed end is, whether it is a secured fixed end, if it's a loose fixed end. Um, Remember, there are different ways that these waves, these pulses can reflect back. So in this picture right here, this is where we have a fixed closed end. So meaning that the here my wave operator is going to be down here, and then this is it's securely tied to, let's say this is a wall. So the wave is going to travel down the string. It's going to hit this location right here, and then we will see this guy right here. It's going to invert and reflect back to the wave operator that's down here. So that's in contrast to if this were a loose end right here. So if it was loose, what we would see is the wave would come down like this, but instead of it seeing inverted, we'd see it look like this. Okay, it would come back just upright and reflected. So remember what this basically is. This is the difference between transmission. Okay, here we have the transmission heading towards the other end versus reflection here. Okay, just kind of write those in real quick. So we have transmission versus reflection. Okay, and the reflection will be an inverted version of the incoming wave. Remember, this is when end is a fixed position, when end fixed position. Okay. Whoop. Okay, and then there was part of all that interference. There was a difference between constructively and deconstructive and constructive interference. So you have constructive right here, where if you overlay two different waves on top of one another, when they come together, they are going to add together, and they're going to make what's called a super, in this case, a super crest. You could do the same thing, only with, let's say, if this was flipped. So if you had a wave look like this and another wave look like this, what that would yield? Well, it would just yield this. It would create a super trough. They would still add together. Okay. And then here we have deconstructive. So this is where we have a crest and a trough, or a trough and a crest, adding together to basically cancel each other out. Okay. So in the form of sound waves, how does this relate to sound waves? So in sound waves, what we would see is that when we have constructive interference, we would have an area where the volume of the sound would increase. For deconstructive, fully deconstructive interference, this is where we would see the volume was pretty much close to zero. We really wouldn't hear anything at that position. Okay. So that's the difference between those two. Okay. Now, this all has to come together in the form of standing waves. And what are standing waves? Well, these are waves of equal amplitude and shape traveling in opposite directions. They meet together, and they more or less come together and combine in particular locations. They're a combination of constructive and deconstructive interference. Because when you send energy down the slinky, the string, the whatever your medium is on a fixed end, it just doesn't go away when you keep adding energy. Like, it's still going to reflect, and then it's going to hit your hand, and it's going to continue to reflect back and forth, back and forth, back and forth. And you could say that it almost reaches a point of like equilibrium. Yeah. It reaches a point of equilibrium. And at that point of equilibrium, more or less in a particular way, you make these standing waves, and they look like this. Okay. And so, like it says here, due to deconstructive and constructive interference, the wave has the appearance of standing still. So I know this looks weird. You're probably thinking like, wait a minute, how does that work? How could we have a wave that looks like this? And so it would be like this. So here is an example of where you would have basically a standing wave generator, where you have these like positions right here where it's being pinched, and then you've got these positions right here that are like these bubble looking things. Now, both these guys down here, these bubble portions, and then these pinch positions have a particular name. Okay. Oh, nope. I want to move on, please. And those particular names are these. The portion of the wave that remains still, the pinch positions, are called nodes. Okay, these are called nodes. Little dots that are, again, pinch positions that are pretty much on the equilibrium position on the medium. So if you were to, and we can use these to measure the wavelength, the frequency of a particular wave, and also the speed of a particular wave. So nodes are spaced, two nodes. I should add that. So two nodes. So when you have two nodes, the space between those two nodes is roughly equal to half of the wavelength of your wave, which we'll see a picture of that in a second. That'll make more sense. Therefore, the distance between three nodes will be equal to, and right here, three nodes will be equal to one full wavelength. Areas in which contain supertroughs and supercrest are called antinodes. Okay, so let's say this. So here we have the nodes, these positions right here, and then you have the antinodes, which are the bubbles. It's these positions right here. Now, they're not counted separately. I know that there are these blue dots and red dots. Ignore the color differences here. It's just to show basically two different waves coming together. You could maybe say that, or just trying to make sense of what your eyes are seeing when you are making the standing waves, because again, it can be moving so fast that it gives the impression of looking like this, when really it still just looks like this, but it's oscillating so quickly that your eyes are deceived and thinks that it looks like this. Okay. So anyway, so this whole position right here is an antinode. This position right here is a node. Okay. So that leads, my goodness, stop yawning. Excuse me. This leads to check your understanding number 1 and number 2, so make sure you answer those. Okay, so the frequencies of the standing wave on a particular string are called, of course, it's supposed to say resonant frequencies. I don't know why. Here, let me double check. I'm going to quick double check everything to make sure it's filled in. I don't know what's happening. Okay, for whatever reason, it's just this one. These are resonance frequencies. Oh, that's not how you spell frequencies. Jeez. So these are called resonance frequencies. Okay, they are referred to, in other words, as either fundamentals or harmonics. So these resonance frequencies are particular frequencies, frequencies of standing waves. So let's first identify the pieces of a standing wave again first. So here we have an example where, in this case, we're going to make standing waves by a dude pulling on a string that's attached to fixed positions. So the distance between where they're fixed is L. This is the length, the distance between both fixed ends here. Okay, this whole thing is L. Okay. So when we only have one antinode, but we have two nodes. So we've got a node here, we have a node here. We have a single antinode. We call this the first harmonic, or we call it the fundamental. Here we have the first overtone, or the second harmonic, which has three nodes, and it has two antinodes. Okay. And then there is the second overtone or the third harmonic, and this guy has 4. This one has 4 nodes and 3 antinodes. Okay. So what do we do with all this information? Well, what we can do here is that when you're asked about the first harmonic, if you're told, the first harmonic in the standing wave has a length of x, it has this length. What's its wavelength? You can find the wavelength by doing this. You can say, well, all right, well, there's 2 nodes. Okay, it's not really a full wavelength, but I know that we could make a full wave, but how much do I know? Or how much would we need? And we would need, say, another full wave like this. Why? Well, because this is only half a wavelength. Okay. Here we would have a full wavelength if it continued like this. And really the distance from here to here is roughly about the same from here to here. Okay. Again, the distance from here to here is roughly about the same from here to here, 2L, one full wavelength. Okay. And then we go to the first overtone. Okay. Where in this case, we have 3 nodes. We have 3 nodes. And this is going to be a full wavelength here. Okay, this is going to be a full wavelength. How? Well, because we can do this. Boom, that's one full wave right there. Remember, this is a wavelength we have. If we're starting here, this isn't a full wavelength. Starting here and moving all the way out to over here is a full wavelength. We're coming back to where we started, and we'd start over and have another wave come out like that. Okay. So again, this right here, the distance from here to here is equal to the wavelength. Sorry, got some. And then the third harmonic here, we have a couple overtones. We got a couple of antinodes. We have specifically 4 nodes. And if we wanted to find the wavelength, we would find it using this equation right here. 2/3 of L. How is it 2/3 of L? Well, easy peasy, man. If this is one wavelength right here, that's one full wavelength right here. Okay. We've got this bit that's left over. And we see here that one full wavelength will take just 2 antinodes, and then you have one left over. Well, if the distance from here to here is 3 of these, and they're all the equal size, but only 2 of them give us the wavelength, well, of course, 2 over 3. 2/3 of the space between here and here is what we use for the wave. Is what we would measure for the wavelength. The other third is just starting a new wave, man. Okay. So here again, the wavelengths of standing waves are seen through this equation, 2L over N. So this is just L is equal to the distance from end to end. N is the number of antinodes. So if you know the number of antinodes, if you know the length from fixed end to fixed end, you can find out what the wavelength is. Using a very, very similar equation here, we could figure out what the frequency is using pretty much the same equation. And so the frequency is going to be this. It's going to be f of n. The frequency is equal to the number of antinodes times the wave velocity divided by 2 times L. Okay. So here's number 3, number 4. So then, silly question. If a tree falls in the wood, does it make a sound? Of course it makes a sound. Just because you don't hear it doesn't mean that there isn't a sound that's being made. And I noticed that this GIF's not working the way it's supposed to, which is really, really odd. Whatever. Oop. So just because you don't hear the sound of a tree falling, it doesn't mean that tree didn't fall. Of course it fell. Because all sound is vibrations. So sound is simply transfer of energy by vibrations between particles within and across mediums. Okay. Now, this video right here, I recommend that you watch this. It exemplifies a lot of really cool things that can be done with sound waves and kind of refreshes them what they are. So give that a watch when you're while you're watching this as well. So, as a good example of really showing how sound waves are produced, sound waves are longitudinal waves traveling through a medium, and we can use a tuning fork to really exemplify that. So, when you strike a tuning fork, this is what happens. You're going to have pretty much the arms are going to kind of come in this way, and then they're going to, this is like them vibrating, and then they're going to push themselves out. They're going to go, and they're going to do that over and over and over again. They're going to come in and out. Now, the only thing is, this picture is quite exaggerated. It's not going to do it as much as that, but really, if you had a really nice macro camera, you could really zoom in and show just how much they're really moving back and forth. So you hit the fork, and it causes the arms to vibrate back and forth, and the outward movement pushes the nearby air molecules away. This is a compression. Okay. When the arms come back together, the air molecules move back to the original spot. This is rarefaction. Okay. So it's going like me, right? That's what's happening here, and that's how sound is produced. That is more or less how sound is produced, using your voice box, using the air pushing by your voice box. It all starts with a vibration, and we can measure and have a better idea of what's happening by transforming these longitudinal waves into sine waves, into transverse waves. So here we have rarefactions. They're considered to be troughs, we'll say. And these signs of compression right here, these locations of compression are crests. Okay. So we can take this data, we can take this physical form, and we can change it into basically an electronic form, and we can show that on things like oscilloscopes and other mediums, other digital devices to show the ups and downs of sound waves in the air. Excuse me. And we can do this, and this is and how we can kind of take advantage of the technology that we these particular technologies is that we can use them in order to make, say, noise canceling headphones. So give this a watch. It walks through. James May walks through how these particular devices, these noise canceling headphones, work. More like real cliff notes. There are microphones in the headphones that will pick up particular sounds, match the frequency, and then deconstructively obliterate that sound, and only leaving whatever sound you want to hear on the inside of your headphones. It's really cool. So, speaking of being able to hear things, there are frequencies that sound waves are transmitted that we can't hear or we can hear. So audible waves are the ones that we can hear. And normally for humans, we can hear between 20 hertz to 20,000 hertz. Anything below 20 hertz, we refer to as infrasonic waves. These are guys that are super low, that is very difficult for us to hear. Earthquakes are an example of this. That's why when you see like dogs, cats, or if you've seen this in documentaries, dogs and cats will freak out. Cows will freak out. Horses will freak out when an earthquake is happening, or at least right before we can really feel and know it's happening. They'll start freaking out. And it's because they can pick up the sound waves. They can pick up the frequency either by hearing or by feel on the ground, and they go berserk, and they try to find a safe place for them to basically hide. We unfortunately cannot hear it because it is below the frequency that we're able to hear. Our ears just are not equipped to pick up those noises. Then there's ultrasonic waves. So this is anything above 20,000 hertz. So ultrasonic would be like ultrasounds. So when you or anyone you've known before, ladies that you've known before who were pregnant that went in for an ultrasound, what they're doing is that more or less the little thing that you slather all that petroleum jelly on, what that's doing is it's shooting sound waves more or less down into her belly, into her womb. Sound waves are going to hit the objects in there, and they're going to reflect back. And then there's a little receiver in the handle, and the receiver is going to take that data, and it's going to more or less create an image, a digitized image of the baby, of the particular of the lady's womb, and that's where we use ultrasound in order for our benefit. There's also dog whistles. Dogs can hear dog whistles. We can't, just because they're way above, the frequency's way above from what we can hear. Now, personally, I'll tell you that, or first I'll say that the average ability, I think, of humans being able to hear higher frequencies is decreasing for a number of reasons. One of them being is the introduction of earbuds into the music market. Myself being included, as far as, I don't want to say victims, but just individuals who have lost a decent amount of hearing because they did not take warnings early enough and seriously. So I can only hear up to roughly about 15,500 on a good day, maybe 16,000 hertz, when I should be able to hear up to 20. So a mixture of listening to too much loud music through earbuds, and being around large farm equipment and not wearing hearing protection, I think have contributed to me losing a substantial amount of my hearing ability at a fairly young age. And I think that's something that we're seeing, and that is seen across the board. I think that's just the more there's AirPods, the more that there's in-ear earbuds, and kids and just individuals playing music crazy loud is ultimately just really, really hurting your ears. And hopefully at the end of 7.3, we'll be able to go into a little bit the anatomy of the ear and really what's happening. But yeah, you're killing off cells in your ear. And those cells don't come back. And when they don't come back, you lose your ability to hear higher frequencies, just a different range of frequencies. Now, so that's frequency in sound waves. Then there's also speed of sound. Speed of sound is altered by how hot or how cold it is, really how much energy is within the air. So we can calculate that using this equation here by saying that at 0 degrees Celsius, or at 273 Kelvin, air is going to move roughly about 331 meters per second. And anything above that, anything above 1 degree Celsius, anything above 273 degrees Kelvin is going to increase our sound speed. And then anything below 0 degrees or anything below 273 Kelvin is going to decrease our velocity. Now, we would need, with this equation I just had up here, we would need temperature in Kelvin all the time in order to use this. So I've got this one instead. So when we calculate the speed of sound in the air per a particular temperature, we're going to use this. We're going to say that at 0 degrees, this is how quickly sound travels through the air. But again, every degree above or below, it's going to alter the speed of this guy. So here we're going to say 0.59, any temperature above 0 degrees Celsius will increase the speed by 0.59 meters per second per 1 degree Celsius. Anything below 0 degrees is going to decrease. It's going to decrease our velocity by this much. So here, as an example, at 20 degrees Celsius, which is roughly about room temperature, our velocity is only going to be 343 meters per second. Okay, and then you go ahead and work on these, check your understandings. And then there's just a couple of things to leave off with you here. So there's loudness. These are ways that we can, characteristics of sound. We characterize sound by its loudness, by what's called the beats, beat frequency, and then also timbre, dissonance, resonance. There's a number of ways that we can describe how a particular sound is. So loudness is related to the intensity of the sound wave. As volume increases, amplitude increases. So loudness is just how much sound is coming out of it. What's the volume set at? So again, when the volumes increase, the amplitude has been increased. And so this is why we call amps, is that they increase the amplitude of particular sounds in order to amplify them, to make them louder, or to make them can make them softer in a certain way. It's kind of weird because you don't really you don't speak into a microphone and expect sound to be softer than what you put in, though that can be the case depending how far away you are from a set of speakers. But anyway, so we can categorize the sound by its loudness. We can also categorize the sound by the beats that it makes. So the beats are not going to be your traditional things and sounds that you hear that keep tempo in a song. Beats are alterations in loudness due to interference. Okay, so I have a demo in class that I'm now realizing I don't have with me here at home, but I do have one in class that shows how beat frequency works. I'll recommend that you just look up beat frequency or how to measure beat frequency. And there should be a number of YouTube videos that walk through exactly what that is and what it sounds like. But anyway, it's where waves have slightly different frequencies and the time between constructive and deconstructive interference alternates. So if I were to play with like a tuning fork, if I were to play two tuning forks that were really, really close in their frequency, but they're just like different enough. What you'll hear like a like you'll hear like the volume increase and you'll hear it kind of decrease and then you hear it increase. And so what you're hearing is you're hearing these two frequencies overlaying one another and they're constructively and deconstructively interfering in particular positions, and they're trying and your ears are trying their best to pick up on what's happening. And you can actually figure out what the beat frequency is by just taking the frequency of one of those objects and the frequency of the other, subtracting them, finding the difference. Okay. And you can find the frequency difference between both of the frequencies, and it would translate like this. So if this is like, say, two tuning forks that you played with slightly different frequencies, they would you overlay them. Here's one black, here's one that's blue. Here you would see they're going to come together in almost perfect constructive interference. There's going to be positions where they come together as almost perfect deconstructive interference. And we can take this data and we can translate this into standing waves. And here we can see that on a standing wave, here the amplitude is the highest. This would be our antinode right here. And here the amplitude is the lowest, and that's going to be our node on the standing wave. Okay, our super crest and super crest right here, and our here would not be super troughs. In this case, it would just be, cancellations, deconstructive interference. Okay, so complete this, check your understanding, and then watch the video so you get it. And then the last characteristic of sound to talk about is timbre. So in music, the characteristic sound of any instrument is referred to as the quality of sound or timbre of the sound. The quality depends on the mixture of harmonics in the sound. But that's just a fancy way of saying that timbre is how warm, how soft, how sharp, how harsh you're making the music sound. And it relates to how well you're able to match particular frequencies up and how much you can dampen what's called dissonance or increase it when you want to increase dissonance. So dissonance is really what beat frequency is looking for. The higher the beat, or sorry, the higher the beat frequency, the higher the dissonance, roughly speaking. Um, the dissonance is where you have two sounds that don't have the same frequency and are going to make quite a noticeable or it's going to make quite a noticeable beat. And Problem with that is that naturally your ears do and your brain do not like the sounds that makes. Now there are musicians that purposefully try to uh, get rid of as much dissonance as they possibly can to make it as soft as they can, to make it as crisp as they can. And Whereas some want to increase the amount of dissonance because what they want to do is they want to make spooky sounding music, and so that's stuff like horror movies. That's or just any kind of movie where you want to shock an individual using music. Shock and to make them uncomfortable, because there's just a natural sense in humans that you can hear even if you're not musically inclined, that certain sounds make you feel a particular way. That's why there are soundtracks in movies, because a lot of times a lot of those soundtracks are trying to make you feel a particular way. Even if you don't know what really to call particular little sections or what they're doing, you just know that if you hear a sound that does not go together, you like your body, your brain naturally says like something's wrong. This feels wrong. I feel uneasy. It's actually really cool. So anyway, but these are just ways that we can characterize sound, and that's pretty much it. Oh, and then there's pitch. I almost forgot about pitch. Pitch is related to mainly, although not completely, the frequency of the sound. Generally speaking, the higher the frequency, the higher the pitch. Lower the frequency, the lower the pitch. But pitch is really just a way for us to talk about and to describe what the sound sounds like and how we can kind of fluctuate between the different frequencies of a particular note. Frequency is a stimulus and pitch is the response, you could say. Okay. So it is a physiological reaction that allows humans to place sound on a scale. That's really what it is. It's a human construct. But anyway, so that is the notes. Make sure that you watch any of the videos that are attached to the Google slide. Also, go back and make sure you got all the correct or make sure you have all the check your understandings correctly inputted and correctly done, and that's going to be it. So that's it for the notes, guys. So if you have any questions for me, make sure you reach out. If not, I'll see you in the next one.